Hello, my name is Wei Chen from NEC Labs at Princeton. And today I would like to share our work on the ranking causal anomalies via temporal and the dynamical analysis on vanishing correlations. So this paper has won the best research paper on the award, so thanks to all my co-authors. So basically, nowadays we are surrounded with a lot of complex systems, such as IT systems or the cyber-physical systems. Here we only list a little bit examples, like the Internet of Things, or the computer networks, or software systems, and the nuclear power plants, and so forth. And one important task for the complex system automatic management is to do the anomaly detection. The straightforward method, for example, the operators can set a bunch of rules and to check and give the trigger alerts if necessary. So here is one example. If, for example, the CPU usage by the web server is larger than some threshold, and the system can trigger some alert. However, such kind of rule-based management needs a lot of domain knowledge. However, in a lot of applications, such kind of domain knowledge is hard to touch. So, and the question coming back, is there a way that we can achieve the automatically or purely data-driven method? In the past decade, our colleagues at the NEC Labs at Princeton is trying to solve this problem. So the format of data set we are trying to address is to the time series data. For example, like the IT systems, we can monitor the flow intensity of the system logs. And for the cyber-physical systems, we can make use of the sensors to monitor the status of each devices, like the temperature, or the speed, or the pressure, and so forth. And although we can keep tracking individual features and to do the anomaly detection, however, we observe that the single time series or the first order feature of the single time series is not that stable, and it's because the real values are keep changing. So by contrast, we observe that the hidden dependencies, or say the hidden relationships between system invariant between different components are more stable, and we will prefer to use to profile the system and check the system status. So we refer such kind of hidden dependencies between different components as the system invariants. So to infer the correlations between different components, we can, for example, we can use the linear autoregressive model with oxygens, or say AIX model. Here, for example, if we want to infer the relationships between time series X and Y, we can use this formula. The model tolerates the possible time delay. So, and with the least square estimator, we can infer the parameters of the regression. So if the fitness score, the formula shown below, is larger than the threshold, we can claim that there exist one correlations between two time series. So based on the system invariant, and we can arrive at our automatic system failure management. And the workflow is shown in this figure. And the first step, for example, is to extract the pairwise dependencies during the AIX model during the system operational normal time. So here, in this figure, we use the red arrow to denote the inferred correlations, or say system invariant of the whole system component. So during the system running time, we can keep tracking the status of those invariants, if they are broken or not. So in this figure, for example, we can make use of the circled row to denote the broken invariant. So once we have obtained the system has detected the anomaly, the subsequent task is to do the diagnosis. So, and the most importantly is to localize the root cause, or say the trigger component. So in this case, for example, it's very easy to infer, because it's most suspicious root cause is in the center, because all the broken invariant is connected to. So it's are all broken. So we'll see that in this case it's very easy. So then we come up with our probability definition. So, and our task is to make use of the topological of the inferred system invariant network and the broken status during the system testing time. and to try best effort guess what is the most likely root cause of the system. So there is one straightforward method to achieve that. For example, some methods in previous works are listed them here, and they make use of, for example, like the percentage of the vanishing correlations as a ranking policy. So, however, so this policy is not a very good one because, so ideally, if there exists, even though the one broken edge is the indicator one, at least one of the nodes it connected to is abnormal. However, if, for example, if the edge is not broken, it's not necessary that all the nodes it connected to are not abnormal. So it's possible that the output of one node is the input of another node. So even though one of the nodes is abnormal, still the correlations between them may still exist. So here we visualized one real example from one of our customers' data. So this is a coal-power plant data set. So totally there are thousands of nodes that indicate that we have thousands of time series. And to zoom into the root cause, we also visualize the one nearest neighborhood subgraph surrounding with the root cause here. And we mark the broken edges within this subgraph. And you will see that the number of the broken ratios for the root cause here is not that high. By contrast, another non-root cause here, the broken ratio is 100%. So, and another important thing, such kind of method cannot tackle is it's not able to model the potential failure propagation. So it's intuitively the root cause will happen and then propagate to the whole network and trigger the alert of the system. So here, for example, if the root cause show in this snapshot time 1, and it propagated to its neighbor, and with time evolving, it will keep evolving to keep propagate to others. So the intuition is that if we can jointly consider multiple snapshots for the joint analysis of the root cause, based on this intuition, so we come up with our algorithm that is able to model the fault propagation. So here are some important notations. So if we use the matrix A to denote the adjacency matrix of the invariant network, and P to denote the broken status of the system invariant. And here, the intermediate variable here, R vector, is used to denote the propagated abnormal score vector. And the vector E is used to denote the ranking score vector of the root causes. And the idea is shown here. So for each broken edges, so intuitively, at least one of node, it should be abnormal after the failure propagation. So then in the production of the abnormal score of the two nodes should be somehow large. For each broken edges in the broken invariant matrix P, the corresponding production of the two nodes should be somehow large. So there we can, for example, we can try to reconstruct the broken status. So then we here have the reconstruction error here. So here, the element-wise production to the logical matrix of the invariant network is to try to rule out the values that is not shown in the invariant network. And so here, the objective function is try to infer E. However, so we need to know the relationships between the root cause vector and the anomaly score vector of the propagation R. So to achieve that, we can make use of the idea of the label propagation. So we're assuming that the root cause we already know, for example, in this figure. As we all know, the failure will propagate to the root cause neighbors. So, and with this objective function, the first part, for example, is the smoothness constraint. That is to guarantee that the abnormal score for nearby nodes in the invariant network should be as close to each other as possible. The second part is the fitting constraint. And this formula has a closed form solution. And this indicates the relationships between the initial root cause and the anomaly score vector after propagation. So we can substitute this part to as an objective function, and we can achieve our final objective function. And ideally, the vector E should be the binary and the sparse, because at each time point, the root cause should be the number of root cause is not that large. But the binary, if we use the binary case of E, that the problem is hard to solve. This is NP hard. So we relax that by make use of the L1 penalty on E, so that the matrix is sparse. And this objective function can be optimized using the multiplicative updating schema, and the formula is shown below. So here, we further talk about some other properties regarding to the algorithm. So previously, we make use of the production of the abnormal score of two nodes to recover the broken edges. However, it suffers from the extreme values or the outliers. To alleviate, we can make use of, for example, like a softmax function to normalize the anomaly score vector E, and substitute this part into the previous formula. We can achieve, we can arrive at an objective function. So another issue is related to the scalability issue. So in previous slides, we needed to calculate, for example, calculate this inverse here, and the production of two n by n matrices. So the time complexity of them is cubic. So to reduce the time complexity, we can relax the problem to infer both root cause ranking vector E and the intermediate variable vector R. So we can avoid the calculation of those two steps. So we can reduce the time complexity to the quadratic. So another issue is referred to the temporal smoothing. So as we shown before, so during a short time period, the root cause should be stable. And based on this intuition, we can jointly consider multiple snapshots together. So that is, we jointly infer multiple rankings vectors for multiple snapshots, and then to guarantee that the nearby ranking vector should be as similar as possible to each other. To validate the proposed algorithm, we make use of two real data sets. And those data sets are from our customers. For privacy issue, we cannot reveal the name of the company. But the first data set we make use of is the coal power plant data set. And that is the cyber physical system. And we use 1 week monitoring data for training and the testing on the lab, on the remaining data set. And the root cause is from the customer domain expert. And the second data set we make use of is the bank information system. And this is the IT system log flow intensity. So, and the root cause is also from our customer. So here we list some examples of the category of the IT system data set, such as CPU usage or the I/O waiting time, or some properties referred to the networks or system or memory, disks, and so forth. And the summary of the two data sets is in the table here. So generally we have thousands of monitors, or say the time series for both data sets. And here we also list the number of invariant links and the broken links. We make use of the precision recall of the top reported results, and also as the NDCG as the comparing metrics. So then we report the results of the first data set. Here, so the first three methods are baseline methods. They more or less make use of the ratio of the broken edges. For example, some methods directly use this broken ratio as the ranking criteria, and some use them as the broken ratio within equal network. the Markov random field method, LBP, make use of the broken ratio as the prior status. And the last 4 methods are the proposed method. So we will see that the proposed method all rank the root cause from customer the highest rank. And so from this, I have shown in previous slides of those 2 figures. So this is zoom into the root cause subnetwork surrounding with the root cause, because you will see that the number of ratio of the root cause is not that large. And but another node here, for example, this is 100% broken ratio. So those baseline methods all rank this node higher than the real root cause. So here we report the results on the bank information system data. So before report the results, we take a look at we randomly select 4 of the time series and related to the root cause, DB16. And we also use the red point to mark the time that the system reports anomaly. So we will see that at the red point, all the time series suddenly increase or decrease. So some events should really happen. But we will see that there are much more such kind of cases. So then it's good evidence that to monitor single time series, it's not that easy to get such kind of to reduce the false positive rate. So there are a lot of false positive cases if you only focus on the monitoring of single time series. So here are the results on the precision recall and NDCG of the different curves. And also to zoom into the results, we also report the top-ranked anomalies reported by different algorithms. And you will find that the proposed algorithm outperforms the baseline method. And another observation we can obtain is the method with softmax normalization is better than the method without normalization. This is where it illustrates the effectiveness of the softmax normalization to rule out the extreme values. And also, the method, relaxed method is a little bit worse than the method without relax. So, but as have shown here, the time complexity or the time consuming of different methods. So for all the relaxed method, start with R, using much small number of seconds compared with the method without the relaxer. So let's report to the effectiveness of the temporal smoothing. Before we look at the final results here, we first take a look at the performance comparison between 2 different time snapshots. The first time snapshot, 120, is the real the time that the system trigger alert. And with time evolving 2 time points later, so we will see all the methods will decrease their performance with the time evolving, because the failure will propagate to the whole network, and it's harder for all algorithms to detect the root cause. However, we found that the proposed algorithm is less sensitive to the propagation of the failure. So this will illustrate the effectiveness of the of our propagation-based model. So here we compare the method with or without temporal smoothing, and we will find that the method with temporal smoothing report more related root cause related results. So this will illustrate the effectiveness of the temporal smoothing. So to conclude this talk, basically in this paper we propose a network in diffusion-based framework and try to solve the causal anomaly ranking problem on the monitoring data of distributed systems. And the proposed algorithm can model the potential failure propagation by minimize the reconstruction error. And the method to real data sets will illustrate the effectiveness of the proposed algorithms. So thanks for your attention. Any questions?
Okay. Hi, thank you for the great talk.
Thanks.
Could you go back to the slide where you're introducing the objective function? Yeah, this one. So what is the...
What happened?
Spaceship is landing.
Okay.
What's the logical matrix here, and how are you calculating that?
Okay, so the logic matrix is just the binary case of the matrix, adjacent matrix A. So we just want to rule out that the values that is not show up in the adjacent matrix. So if the adjacent matrix, for example, A is the binary one, then A and M is the same.
And yeah, okay, go ahead.
So, question: if this is like a network in a company, then if I turn off my portable, it disconnects from the network. It's not an anomaly. Or if I work with a security operations center, they take nodes down on all the time on scheduled maintenance, and it's not an anomaly. Am I misunderstanding about what this matrix is? Is this computers connected to each other?
So you mean the problem setting, right?
Yeah, like A.
So okay. So for the problem setting is that, for example, we have a large-scale distributed system, or or even you can monitor the single system, and this one system contains a lot of different applications, like for example, like database or web server, or Archer Office, or a lot of applications, and you can monitor, for example, the flow intensity of system logs, such as the CPU usage by some specific applications. And then you can get the time series data. So the task of the algorithm is to, if the system is abnormal, and if we can, as early as possible, report what is the most likely the trigger application. Or in cyber physical system, there are a lot of devices, and those devices are connected to each other and has some dependencies to each other. So, and once we have observed the system is abnormal, and we want to zoom into what is the most suspicious root cause, this is our problem setting.
Okay, let me just talk to you offline.
Thanks for your question.
Yeah. Okay.
Thanks for the great talk. I think in practical world, certain things that we have seen is when systems like malfunction in terms of CPU or memory, sometimes the behavior is just with a steep curve. We even don't have time to react. Like all of a sudden we'll have in the time series data, everything is normal. And then all of a sudden we see the huge spikes. Do you think this will really help detect that, or do you have like a period by which you need to actually have time to react before your system reports? Is what I'm trying to understand.
So good question, really. So actually, this problem is very, very hard because the system is quite dynamic. So, but as we have mentioned before, so even though some event happened, or for example, like the CPU usage significantly increase, but still maybe some correlations between the different components still exist. Yeah. And so the focus of this paper is on the root cause ranking, not the anomaly detection. The first step is anomaly detection. So you can, using a straightforward method, for example, if the broken edges reach some threshold, and then you can report the error. So actually, our system, this is only part of our final system. So we have a thorough solution for that. For example, like the single time series trigger monitor, like the periodical properties or the constant with some noise. And also, this is a second order. And we can also have some high order, like the cluster property. If, for example, if some member previously in cluster, but suddenly disappear, then this is another abnormal. So this is a joint solution to the whole problem. This is just one piece of the cake. Okay.
Quick question. In the precision and recall graphs, from what I could see in the precision graph, the precision around, let's say, at 12 was around 0.5, around something like this. What is the balance between anomalies and regular events in the dataset? What is the percentage of anomalies?
You mean the percentage of root cause, right?
Was it so? There was a figure showing. I'm not even.
Yeah, I see.
I don't even remember was it a root cause or was it the number of anomalies found? I'm not.
Okay,
sure.
so this is related to the the bank information system dataset.
Yes.
So because the system expert only gives us that the system abnormal is related to database 16, but the database 16 has, for example, almost 50 or more related records, different categories. So it's we do not have the real answer. What is exactly the root cause? But we only roughly rank all the database 16 related as the ground truth. This is our solution.
All right. Thanks.
Thanks.
Okay, one quick question here.
Thank you for the nice talk. A quick question. What happens if the fault is at the edge of the network?
Sorry?
What happens if the fault is at the edge of the network? That means when it faces outside, so all the internal correlations still behave okay, but maybe you don't observe something coming in even.
So it's possible. So for example, and I think so it depends on different system you are addressing. So for example, if the system all is the input of one node, then output of another node, then even though one node is abnormal, still the correlation between them still exists. But this kind of thing is very, very hard to tackle. So.
Okay, thank you.
Thanks.
Let's thank the speaker again.